Now moving on to our next problem, that is Leetcode problem number 2493, which is marked as a hard level problem on Leetcode. Divide nodes into the maximum number of groups. So you're given a positive integer n representing the number of nodes in an undirected graph. The nodes are labeled from 1 to n. You're also given a 2D integer array edges where edges of I is equal to ai comma bi, indicates that there is a bidirectional edge between nodes ai and bi. So it's an undirected graph. That is why we have a bidirectional edge, right? If you draw this or you basically draw this, it means the same. There's a bidirectional edge. Notice that the given graph may be disconnected. So we may have more components, right? Let us say this is the graph and we may have other components. So this is the whole graph and it is disconnected. It may be that may be possible. So we'll have to traverse through all the nodes, right? Now we need to divide the nodes of the graph into m groups, one index, such that every node in the every node in the graph exactly belongs to one group. So it means he's trying to say is that what this problem is trying to say is that each node in the graph belongs to exactly one group, right? And for every pair of nodes in the graph that are connected to an edge, connected by an edge ai comma bi, if ai belongs to the group with index x and bi belongs to the group with index y, then y minus x mod of this is equal to 1. So absolute of this is equal to 1. That means the edge that is connecting it, the index of this edge and the index of this should only differ by 1. Now we need to return the maximum number of groups, maximum m, into which you can divide the nodes. Return -1 if it is impossible to group the nodes with the given conditions, right? So let us say this example. So we draw this graph, we get this graph. So basically the edges are in this format, right? So you see that we have divided into 4 groups. We can see that every edge has been satisfied, right? So this is 1, this is 2, this is group number 3, this is group number 4. You can see that any node that has already been connected by an edge does not fall in the same group, otherwise it would not satisfy the condition. And if we have something like this, that means they are not connected, these nodes are not connected by an edge, so they can belong to the same group. That is our first observation of this. Similarly here, there's no edge here, so basically they can be considered into the same group, right? If we create a 5th group and move any node from the 3rd or 4th group to it, at least on one of the edges will not be satisfied in this example. So now let us take you over to the solution. So easy BFS and bipartite. How do you think? How do you reach to this thought process? So let me go over the intuition. So we're given a graph with n nodes, one indexed in input, converted to 0 indexed internally and edges. We need to split the nodes into groups or levels such that each group contains nodes from a BFS traversal level. Adjacent nodes cannot belong to the same group. So adjacent nodes cannot belong to the same group. For each connected graph component of the graph, the maximum number of groups is determined by the largest BFS traversal depth. Maximum number of groups would be returned by the largest BFS depth or the level from any node within that component. Also, if any component of the graph is not bipartite, it is impossible to form valid groups. Return -1. So we have to check all these conditions, and we need to return the total maximum number of groups across all connected components. So bipartite graph property, let me discuss that. A graph is bipartite if we can color its nodes with 2 colors such that no 2 adjacent nodes share the same color. And you can also, I'll remind you that if we have an odd length cycle in any graph, let us say this is the graph that we have. So if in any case we have an odd length cycle, you will see that this will never be a bipartite graph, because bipartite will never be because we have an odd length cycle. So let us say we assign color red to this, then color blue to this, and since bipartiteness is basically we have to assign 2 colors. So if you were to choose red color, you see that this is connected to red, so its adjacent node is also red, so we cannot color it red. And similarly blue is also connected to this directly, so blue would also, we won't be able to color, so we have to bring another 3rd color, that is green, in order to color it. So this may be tripartite, but we cannot color it with 2 colors, that is red and blue, so this is not bipartite. So that is why whenever we have an odd length cycle, we can never color it with two colors. So that is the property, that if we have an odd length cycle, we would it is not bipartite, and if we do have an even length cycle, then it is bipartite, right? So if we color this as red, then this would be blue, and this red, this would be blue. So no 2 adjacent nodes are the same color, if you see, right? So an even length cycle would definitely be bipartite. So that is the property. And if a component is not bipartite, that is has an odd cycle, that was what I am discussing, it is impossible to form valid groups, hence the answer is -1. We return it. Now BFS levels are equal to the groups. So for a connected component, the maximum number of groups corresponds to the height of the BFS tree starting from an optimal node, the one that yields the maximum BFS depth of the level. And we perform BFS from every node in the component to determine its maximum possible depth. Then we have the component wise calculation. So for each connected component that we are considering, we find the node that has the maximum BFS level and add to the global result. Total result would be the sum of the maximum groups from each connected component. Now our approach is something like this. So firstly, we build the graph, use an adjacency list of this representation, an ordered map int comma vector of int to store our edges, convert nodes to zero-based indexing for convenience, then bipartite check, use DFS-based coloring, that is colors of node is equal to 0 or 1 representing the two colors. So we are taking 0 and 1 as our colors. And if we encounter a neighbor with the same color, then false, we return, right? That is, graph is not bipartite if a neighbor is of the same color. Now BFS level for each node, we run BFS and get the maximum depth and store the depths in the vector levels of node, right? So for each node, we are going to store our levels, that the maximum level that we can go to. So for example, this is our graph, right? So levels of nodes I'm drawing. So 0, 1, 2, 3, 4, right? These are the indices. So from 0, what is the maximum level? So this is our level equal to 0, or if we are starting from level equal to 0, then this is level equal to 1 and this is equal to level 2. So we store 2 here, maximum number of levels that we can go. So from 1, if you start our BFS, this is the level equal to 1, sorry, level equal to 0, then this is level equal to 2, then this is level equal to 3, sorry, this is level 0, this is level 1, this is level 2, and this is level equal to 3. So 1 has 3 as the level. Then for 2 as well, if we calculate, so from 2 we have this as level 1, these 3 nodes as level 1, and this is level 2, right? For 4, if we compute, this is at level equal to 2, along with this is being level 2, 2 is at level 1, and this is level 3, and similarly for 4, right? So we store the levels of node basically using by applying BFS on each and every node. Then we process each component for each unvisited node, find the maximum level among all nodes in the connected component using DFS, and add this value to the final result. Complexity analysis for bipartite checking, we basically have O of V plus C. For BFS from each node, O of V times V plus C. Worst case, since we run BFS from each node, so number of nodes that we have is V, which is the number of vertices, and BFS takes V plus C. So O of V plus C, that is our worst case complexity. DFS for each component takes O of V plus C, and the total complexity is coming from here, O of V times V plus C. Space complexity for the adjacency list and the color array and the level array, O of V plus C. So for the vectors, we have that. Now let's get to the coding part. So this is our, let me start from the magnificent set. So basically this is our function that would tell us basically the maximum number of groups that we have. It takes n and edges as our parameters. So we form our adjacency list in this format, and we basically E of 0 minus 1 we are doing because we need to convert to zero-based indexing, and we add our edges to the adjacency list, right? So now we perform bipartite check. So vector of int colors and minus 1. Initially all nodes are uncolored, so we assign minus 1 to each node. So now we traverse for each node. If the colors of node is minus 1, that is, if it has not yet been colored, then we call is bipartite on this node, and we check here itself that if is bipartite returns false, that means the graph is not bipartite. We return minus 1 because if any one particular component in the graph is not bipartite, we won't be able to form those groups. So answer is minus 1. So we return here only, and then we finally get BFS to get maximum levels for each node. So we store levels in this vector. We go over all the nodes and do BFS from each. So basically this takes time V, and inside we are calling BFS, so that takes V plus C. So it essentially takes O of V times V plus C. This is our time complexity. Now maximum groups from each component, we declare a visited vector of bool type. For each connected component, we add the maximum levels of any node in that component. So for the node, going over all the nodes, if the node has not yet been visited, then we get the maximum groups from each component, right? So we are getting the components maximum groups, and then we are adding it into our final answer and returning it. So now let me take you to our BFS first. So BFS, standard BFS we are performing, that is unordered map. We are taking the adjacency list, the current node, and n, taking a queue and visited vector which is initialized with false since no node has been visited yet, pushing the current node and marking it as visited into the queue. We have pushed it and marked it as visited. Level is equal to 1. So basically the maximum groups in that component of graph is being stored by level. So while the queue is not empty, len is equal to queue.size. While len is minus minus, we extract the node from the front of the queue and pop that element out, and we go over all the neighbors of that node, right? So for each neighbor in the adjacency list of node, if the neighbor has not yet been visited. If our neighbor has not yet been visited, we mark it as visited and push this into the queue. And finally, when we get out of this while loop, we increase our level, that is, we have moved to the next level. And finally, we return level -1. So BFS is used to just get the maximum depth. Now, isBipartite is our function which ensures that valid groups can be formed, since only bipartite graphs can be led like in the format that we have. So bool isBipartite is our function which takes the adjacency list, node, and colors vector, and the current color. So current color, we have, it would basically alternate between 0 and 1 to check the bipartiteness of the graph. So initially we color the node and store it in our colors vector. So current color would come 0 1, and we go over all the neighbors in the adjacency list of nodes. So we go over all the neighbors for that particular node. Let us say this is our node. So we go over all the neighbors that are directly connected to it, right? So for all the neighbors, if the color of the neighbor is equal to color of the node, that means if this neighbor, or if this node that has been connected to this node, if both of their colors are equal, that means it is not bipartite, right? Because we need alternate coloring. If this is color 0, then this must be 1. But we are saying that if both of them are equal, that is 1 and 1, so it is not bipartite, same color as current node, not so not bipartite, so we return false. And similarly, if the neighbor is still unvisited, and if bipartite is bipartite, the recursive function returns false, then we return false. And otherwise, if all these conditions are checked and it is not coming out to be false, then we return true, that the graph or the component that we are considering is bipartite. So this is that function. And finally, we have the DFS, which is to calculate the maximum number of groups possible for each connected component of the graph. So maximum group we get from the levels of the current node, which shows the maximum number of levels of the groups starting from the node current. And we mark the current node as visited, right? So this is current node. And then we do perform a DFS across the component and take the maximum levels or the node found. So for each neighbor for each neighbor of the current node, let us say this is the current node. For each neighbor, if it has not yet been visited, then we call it recursively. That means we get the maximum components, maximum from each component, from this component, and take the maximum of this value. Finally, we have to return the maximum number of groups that are possible from current, right? So this is recursively calculating it. Similarly, this would calculate it, and we return max group. So that's it about the problem.